In recent years, the U.S. Navy initiated several programs leveraging autonomous technologies to expand its capabilities and resilience across various applications. The integration of unmanned surface vessels marks a strategic initiative. The program provides the Navy with versatile and cost-effective solutions for a range of maritime tasks. As the U.S. Navy ventures into uncharted waters with the introduction of a brand new $300 million massive drone ship, questions arise about the extraordinary resilience of these behemoths at sea. What specific autonomous technologies are being tested on the new $300 million massive drone ship by the U.S. Navy? How does the integration of unmanned surface vessels contribute to the expansion of the Navy's capabilities and resilience across various applications? Dive with us into the fascinating world of naval technology and discover how drones are being used massively by the U.S. Navy. Unmanned surface vessels. The unmanned surface vessel, or USV for short, is a watercraft that operates without a crew and can have different levels of autonomy, ranging from being remotely controlled to being fully autonomous. It incorporates advanced sensor AI and communication systems for navigation and data gathering. With sizes typically ranging from 45 to 300 feet, USVs are designed to be modular, making it easy to customize them for different purposes. Examples of these include equipping them with surveillance equipment or electronic warfare systems. This versatility enables USVs to be used in a variety of missions, such as surveillance and mine countermeasures. Meanwhile, USVs have a rich history that dates back to the 1920s, when they were first utilized as remote-controlled target craft, following the development of the DCBs during World War I. As World War II unfolded, USVs found application in minesweeping operations as well. In the 21st century, their utilization has expanded significantly, encompassing a wide range of purposes, such as oceanography, environmental monitoring, cargo transport, and military operations. Furthermore, researchers are actively exploring various other potential applications for USVs. However, it's worth noting that some commercial USVs incorporate navigation systems that adhere to the COLREG standards. This ensures compliance with internationally recognized regulations for the prevention of collisions at sea. An important milestone in the deployment of USVs in naval conflicts occurred in October 2022 during the Russian invasion of Ukraine. The Ukrainian armed forces employed a formidable force consisting of 7 unmanned surface vessels and 8 unmanned aerial vehicles in an attack on multiple Russian naval vessels stationed at the Sevastopol naval base. This event, as reported by Naval News, marked the maiden utilization of USVs in naval warfare. Development. Since the end of World War II, the U.S. Navy has been utilizing remote-controlled unmanned surface vessels, USVs, for various purposes, such as target drones and minesweeping. Fast forward to the 21st century, remarkable advancements in USV control systems and navigation technologies have emerged. This has led to the development of USVs that can be operated remotely by an operator from a land-based station or a nearby vessel. Additionally, there are USVs that possess partially autonomous control capabilities, and even those that can operate completely autonomously. The applications and research areas for modern USVs and autonomous surface vessels, ASVs, have expanded significantly. These include their use in commercial shipping, environmental and climate monitoring, seafloor mapping, passenger ferries, robotic research, surveillance, inspection of bridges and other infrastructure, as well as military and naval operations. The versatility of USVs and the continuous progress in their technology make them valuable assets in a wide range of industries and research fields. Computer-controlled and operated USVs. The design and construction of unmanned surface vessels is a multifaceted and demanding task. It involves the consideration of numerous factors and requires the careful analysis and implementation of various elements. This includes making critical decisions related to mission objectives, payload requirements, power allocation, hull design, communication systems, and propulsion control and management. Traditionally, builders of crewed vessels often rely on single-source suppliers for propulsion and instrumentation. This helps the crew effectively operate and control the vessel. However, in the case of uncrewed or partially crewed vessels, the builder must find alternatives to replace elements of the human interface. This involves developing a remote human interface that can effectively fulfill the functions typically performed by a crew. USVs vary greatly in size, ranging from just a few kilograms to several tons. As a result, the propulsion systems required for these vessels cover a wide range of power levels, interfaces, and technologies. Some USVs even utilize electric drives to achieve stealthiness and enhance endurance. While various protocols are employed to control the propulsion systems, it is important to note that many of these protocols do not provide any status information. However, feedback regarding the achieved revolutions per minute can be obtained through tacho pulses or from built-in sensors that generate controller area networks or serial data. To gather additional information, other sensors, such as current monitors, can be installed on electric motors. These sensors provide an indication of the power being delivered. Safety is of utmost importance, especially when dealing with high power levels. Even a small propeller can cause significant damage or injury. Therefore, it is crucial for the control system to be designed with safety in mind. This is particularly important in the handover protocols for optionally manned boats, where the transition between automated and manual control must be carefully managed. One of the primary challenges faced when controlling unmanned surface vessels is ensuring a smooth transition from full astern to full ahead. In contrast to USVs, crewed vessels typically have a detent behavior with a wide deadband around the stop position. However, achieving accurate control of differential steering for USVs necessitates compensating for this deadband. Internal combustion engines often drive through a gearbox, which can result in an abrupt change when the gearbox engages. This sudden shift must be taken into account by the control system to ensure fluid and precise movement. In contrast, water jets adjust smoothly through the 0 point, providing more consistent movement. Electric drives also present challenges due to a built-in deadband that preserves crew behavior, but can lead to choppy or inconsistent movement in automatic control mode. To address this issue, the control system must be designed to smooth out the deadband for low-speed maneuvering and dynamic positioning. Oceanography, hydrography, and environmental monitoring. USVs offer significant value in the field of oceanography. They provide enhanced maneuverability compared to moored or drifting weather buoys, while being much more cost-effective than weather ships and research vessels. Additionally, USVs offer greater flexibility compared to contributions from commercial ships. In oceanographic research, USVs have proven to be particularly useful as they are often powered and propelled by renewable energy sources. For instance, wave gliders utilize wave energy as their primary propulsion method, while sail drones and sail buoys rely on wind power. Some USVs also integrate solar panels to generate energy for electric motors. Notable examples include the Data Explorer by Open Ocean Robotics and Xocean. Thanks to their renewable energy sources, USVs equipped with solar cells can sustain long-term operations in the ocean. The persistence of these renewable-powered USVs is typically measured in months, providing a reliable and sustainable platform for conducting extended research missions. As of early 2022, USVs have primarily been utilized for environmental monitoring and hydrographic surveys. However, it is anticipated that their usage will expand in the future, particularly in the monitoring and surveillance of extremely remote locations, thanks to their versatility across various disciplines. One of the key factors driving the increasing adoption of USVs is their low operational cost compared to crewed vessels. This cost-effectiveness has consistently motivated organizations to opt for USVs. Additionally, the drivers behind USV uptake have evolved over time, reflecting changing priorities. These factors include minimizing risks to human life, achieving spatio-temporal efficiency, extended endurance, precise data collection, and accessing very shallow waters. USVs offer significant advantages in terms of cost efficiency and safety, making them the preferred choice for many applications. Moreover, they excel in areas where crewed vessels may face limitations, such as operating in remote or hazardous environments, as well as efficiently navigating in shallow waters. Furthermore, USVs powered by non-renewable energy sources have proven to be invaluable tools for commercial hydrographic surveys. By employing a small USV in conjunction with traditional survey vessels, these USVs act as force multipliers that significantly enhance survey efficiency. This approach allows for double the survey coverage while reducing the time spent on site. In a groundbreaking survey conducted in the Bering Sea off Alaska, the ASV Global Seaworker 5 autonomous surface vehicle played a pivotal role by collecting 2,275 nautical miles of survey data, which accounted for 44% of the overall project. This marked a milestone for the survey industry, resulting in a remarkable 25-day reduction in time at sea. The successful integration of the USV as a force multiplier conveyed substantial benefits, solidifying its position as a game-changer in the field. Another noteworthy achievement took place in 2020 when the British USV Maxlimer autonomously completed a seafloor survey spanning 1,000 square kilometers in the Atlantic Ocean, west of the English Channel. The completion of this unmanned survey demonstrated the immense potential of USVs in efficiently conducting large-scale surveys, even in remote and challenging environments. USV Sail Drone Explorer. During the International Maritime Exercise Cutlass Express, the USV Sail Drone Explorer was sighted sailing in the Gulf of Aqaba by a patrol craft from the Royal Jordanian Navy. With participation from navies worldwide, this exercise is the largest multinational maritime training conducted in the Middle East. The primary objective of this training event is to foster partnerships and establish smooth interoperability among participating navies. Moreover, it provides an opportunity for nations to showcase their latest innovations and technological advancements in the maritime domain. Once the USV Sail Drone Explorer was deployed into the water, both the Jordanian Navy and the US Navy closely monitored and assessed its performance. The early prototypes of the Sail Drone Explorer featured a narrow hull with support from 2 outriggers. However, the latest design showcases a 23-foot hull with a deeper and heavier keel. These drones rely on a 15-foot wing, which functions similarly to a sail on a sailboat, but is more akin to an airplane wing. By harnessing the force of the wind passing over the wing, the drones generate thrust. Additionally, a small tab attached to the wing's tail controls the angle of attack. Steering is achieved through the rudder, which determines the direction of the hull, while the keel ensures stability. Primarily utilized for scientific data collection and single-beam ocean mapping, the Sail Drone Explorer is designed to serve these purposes. In addition, there are larger variants available. The 33-foot Voyager is specifically designed for maritime security and ocean mapping, while the 65-foot Surveyor is intended for deep ocean multi-beam mapping. Notably, the USV Sail Drone Explorer is equipped with a GPS system and an onboard computer. This enables the vehicle to navigate along predefined waypoints while staying within a designated safety corridor. Importantly, the onboard system autonomously factors in winds and currents to ensure it travels safely and efficiently. Unmanned Surface Vessel Ranger. On September 18, 2023, the autonomous surface vessel Ranger successfully arrived at Fleet Activities Yokosuka in Japan. This important visit marked a significant milestone in Integrated Battle Problem 23.2, a collaborative effort aimed at advancing the integration of manned and unmanned teaming in the Indo-Pacific region. Ranger, alongside several other medium and large unmanned surface vessels from the United States, underwent comprehensive testing during this program. The goal was to harness the potential of these cutting-edge USVs and explore their capabilities in order to enhance warfighting advantages. By joining forces with their esteemed allies, including Japan, the U.S. Navy actively engaged in the process of testing and leveraging the capabilities of these USVs. The ultimate objective was to develop new strategies and optimize the synergy between manned and unmanned systems. ultimately bolstering their effectiveness in combat situations. Before its arrival in Japan, Ranger, an autonomous watercraft, took part in a series of exercises to prepare for its deployment. As an autonomous vessel, it is paramount to address technical issues, ensuring reliability and safety at all times. To achieve this, rigorous testing is conducted in diverse dynamic environments, exemplified by its participation in RIMPAC, the world's largest international exercise. RIMPAC serves as an invaluable platform for integrating autonomous systems with manned counterparts, including various ships, marines, and aircraft. The objective is to foster effective collaboration and communication between unmanned and manned platforms, maximizing their combined potential. This exercise not only serves as a testing ground for the capabilities of autonomous systems like Ranger, but also facilitates the exploration of their seamless integration with their manned counterparts. By pushing the boundaries of unmanned-manned teaming, RIMPAC paves the way for advanced strategies and tactics in future operations. When operating in shallow waters, a distinct hull design is necessary, characterized by a smaller, sleeker, and faster structure. A remarkable example of this is the USV Martax Devil Ray T-38, which autonomously navigates the challenging Florida Strait to reach the west banks of the Bahamas in under 1 hour. During this journey, Maritime Tactical Systems conducted a comprehensive assessment of the speed and accuracy capabilities of the Devil Ray T-38. Notably, the autonomous watercraft is designed to swiftly adjust its course and stop if needed to avoid potential collisions with other boats in the vicinity. While the Devil Ray T-38 may appear smaller in size compared to the USB Ranger, it is important to note that there are even smaller watercrafts in existence. One such example was showcased at the IMX event, highlighting the remarkable range of applications for drones at sea. Common Unmanned Surface Vessel. The Common Unmanned Surface Vehicle, CUSV, is a highly advanced sea drone technology that offers tremendous potential for maritime operations. In 2020, the CUSV underwent an extensive demonstration of its capabilities during Exercise Citadel Shield Solid Curtain. This exercise was primarily designed for anti-terrorism force protection missions, and the CUSV demonstrated a formidable ability to perform this important role. With its advanced features, the CUSV is well positioned to play a crucial role in safeguarding ports, harbors, and other high-value assets beyond the water surface. Its flexibility and adaptability enable it to perform multiple critical functions, ranging from surveillance and reconnaissance to escorting and interdicting suspect vessels. The CUSV is specifically engineered to meet the weight and handling constraints of a typical rigid-hulled inflatable boat. Its hull design ensures excellent seakeeping ability, allowing it to perform reliably in varying sea states. Equipped with advanced controls, the CUSV is capable of autonomous navigation and operation. One notable feature of the CUSV is its adaptability. It can be converted to manned operation by simply replacing its mission modules within a 24-hour time frame. This flexibility enables seamless integration with manned operations as needed, optimizing efficiency and mission execution. Remarkably, the vessels of the CUSV hold the distinction of being the first unmanned vessels to be officially recognized and numbered as ships within the esteemed United States Navy. This recognition highlights the significant advancements made in autonomous marine technology and demonstrates the Navy's dedication to incorporating unmanned systems into their fleet. As a crucial component of the LCS Mine Countermeasure (MCM) mission package, these boats fulfill the role of the Unmanned Influence Sweep System (UISS). They are specifically designed to tow a countermeasure system that emits acoustic and magnetic signals. These signals effectively trigger and detonate influence mines from a secure distance, ensuring the safety of the vessel and its crew. The boats are not limited to this singular function alone. They also possess the capability to carry various other countermine payloads. This includes advanced equipment such as side-scan sonar, as well as unmanned underwater vehicles specifically designed for mine hunting and sweeping operations. Additionally, these boats can transport non-lethal weapons and intelligence, surveillance, and reconnaissance (ISR) packages. Unmanned underwater vehicles. To ensure thorough sea surveillance, the U.S. incorporates unmanned underwater vehicles, UUVs, into their operations. These sophisticated UUVs play a vital role in maintaining maritime security. During the US-UK mine countermeasures exercise, highly skilled UUV operators demonstrated their expertise in launching and recovering the Mk-18 Mod 2 unmanned underwater vehicle. These autonomous vehicles are equipped with cutting-edge sensing technologies, enabling them to navigate deep waters with precision. The primary objective of these UUVs is to detect and neutralize sea mines. With their advanced sensors, they can effectively locate and identify potential threats lurking beneath the surface. By leveraging their autonomous capabilities, these UUVs contribute to enhancing the safety and security of maritime environments. Unmanned underwater vehicles offer a strategic advantage by granting access to areas that can pose challenges for traditional maritime operations. To ensure the utmost reliability and effectiveness of these unmanned vehicles, rigorous testing is paramount. Deploying UUVs in exercises, such as mine countermeasures, MCM, serves as a crucial opportunity for teams to refine their skills and enhance their knowledge. These exercises provide a platform for honing UUV capabilities and optimizing their performance in real-world scenarios. By participating in MCM exercises, teams gain valuable experience that contributes to greater proficiency in operating UUVs. The challenges encountered during these exercises enable the identification and resolution of potential issues, leading to continuous improvement and innovation in UUV technology. Sonobuoys. In tandem with unmanned underwater vehicles, the U.S. Navy uses sonobuoys for comprehensive underwater monitoring. These floating devices, deployed from aircraft, are specifically designed to detect and identify underwater sounds, making them invaluable tools in anti-submarine warfare and underwater surveillance operations. Sonobuoys are compact yet powerful devices equipped with hydrophones that effectively pick up acoustic signals beneath the waves. Once these signals are detected, the sonobuoys transmit valuable data in real time to naval operators. This real-time underwater intelligence significantly enhances maritime security by ensuring timely and informed decision-making. With the use of sonobuoys in conjunction with UUVs, the U.S. Navy achieves a holistic approach to sea mine surveillance and underwater monitoring. The combination of these technologies provides comprehensive coverage and a deeper understanding of underwater activities, enabling proactive actions to counter potential threats. During the Winter Fury 22 training exercise, which focused on anti-submarine warfare and tactical recovery of aircraft and personnel, sonobuoys played a crucial role in collaboration with the Helicopter Strike Maritime Weapons School Pacific. Marine Aircraft Group 39 dedicated their efforts to developing effective tactics for mobilizing the sonobuoys. The objective of these operations was to evaluate the speed and range of Winter Fury 22 in supporting the Navy's anti-submarine warfare mission. The sonobuoy operations commenced with Marines transferring multiple sonobuoys to HMLA and HMLA helicopters in a vast expanse of the open sea. Sailing high above with only the horizon in sight, the helicopters strategically positioned themselves. Once the designated location was reached, Marines manually deployed the sonobuoys one by one at varying distances. These exercises offered Marines realistic and relevant training, ensuring their readiness to effectively respond to global crises in highly contested maritime environments.